Hi there. This will be a review of our acids, bases, buffers, and titration quiz. So I'm going to be going through the questions on the quiz and working those out for you. Alright, so first of all we start off with a strong acid, strong base titration. Hydrochloric acid and NaOH are strong acid, strong base. If we're looking at the pH before any NaOH is added, well, it's very simple. You just take the pH is going to be the negative log of the hydronium ion concentration or the hydrogen ion concentration, and that's just going to be the negative log of the concentration of the HCl, because 100% of the HCl is going to react and form hydronium ion. That's a one-way arrow, not a two-way arrow. So we're going to say negative log of 0.100. The log of 0.1 is -1, so the pH is going to be 1.00 in this case. Now, if we move on and look at the situation after we've added 50 milliliters of NaOH, we're going to have to do a little bit of an analysis here. So our reaction is HCl plus NaOH goes to water, and sodium chloride, that's of course an aqueous solution, liquid water, aqueous NaOH, and aqueous HCl. And we're going to do a BCA analysis of this before, change, and after. We're not going to worry about the water. We're not even going to worry about the NaCl. It's a neutral salt. We're just going to worry about the HCl and the NaOH. And we're going to use millimoles. If I look at HCl, I have 100 milliliters times 0.100 molar. That is going to be 10.0 millimoles of HCl. NaOH, I've got 50 milliliters times 0.100 molar. That's going to be 5.0 millimoles. And if we look at those two, the limiting reactant is NaOH, so all 5 millimoles of the NaOH will react, and 5 millimoles of the HCl will react. That'll leave me 5 millimoles of the HCl and 0 millimoles of the NaOH. So at the end of this, I've got a HCl solution that has 5 millimoles. And that 5 millimoles is now in 100 plus 50 milliliters. So 150 milliliters. Milliliters divided by millimoles is molarity. So 5 divided by 150, the concentration's gone down to 0.033 molar. Our pH then will be negative log of that. So that's going to be 1.47. So we see that the concentration of HCl went down from 0.1 to 0.033, and the pH went up from 1 to 1.47, so it's not quite as acidic, and both of those things make sense. Moving on to the next question, now we're going to take it right up close to the equivalence point. We've got 100 milliliters of HCl, and it's being titrated with 99 milliliters of NaOH. So again, I'll write my reaction equation. I will make a BCA chart here. I'm not going to be concerned about the water or the NaCl, only about how much HCl or NaOH is left over. As we said before, 100 times 0.1, that gives me 10 millimolar. Now we have 99 milliliters times 0.1 molar. That's going to give me 9.9 millimoles. So the limiting reactant is NaOH still. There's 9.9 millimoles of that reacts. So 9.9 millimoles of HCl react, which leaves me 0.1 millimole of HCl. And now we've got 199 milliliters. So our HCl concentration is going to be 0.1 millimole over 199 milliliters, adding those two together. So that concentration .1 divided by 199, that is 0.12305025 molar, so much smaller. Our pH is now going to be the negative log of that. Well, it's basically 5.025 times 10 to the negative fourth. That comes out to be 3.30 basically is our pH at that point. So again, the HCl concentration's gone down a whole lot more. pH has gone up dramatically to 3.30. Now, when we go across the equivalence point, of course, when it's 100, if we had 100 milliliters of NaOH, that would have been the equivalence point. We would have exactly run out of both of those. Our pH would be 7.00. There'd be no acid or base in solution. Now we're going to look, having gone 1 milliliter past, what do we have? So HCl plus NaOH goes to H2O plus NaCl. AQ for the NaCl, liquid for the H2O, AQ for NaOH, AQ for HCl, before, change after. Don't care about water, don't care about NaCl. We still have 10 millimoles of HCl, and now we have 10.1 millimoles of NaOH. You get that by multiplying the milliliters times the concentration in each case. So, like that. So now the limiting reactant's HCl, and we're going to have left over 0.1 millimole of NaOH. So our concentration of OH minus is going to be 0.1 millimole over now 201 milliliters. So that concentration is 0.1 divided by 201. That's going to be 4.98 times 10 to the negative fifth molar. So our POH is the negative log of that concentration. So that is going to be, a pH is going to be basically 3.30 again. To get the pH, I'm going to take 14 and subtract the POH from it. And that gets me basically 10.70. So in the space of 2 milliliters there, the pH jumps from 3.3 to 10.70. Pretty dramatic jump, and that's again characteristic of that strong acid, strong base titration, where we have essentially a fairly slow increase, and then right at the equivalence point it jumps up, where that equivalence point is at 7. And you see 1 milliliter before and 1 milliliter after the pH is relatively low and relatively high. And if we go on and we look at 150 milliliters, we're going to do the BCA analysis again. We have 10 millimoles of the HCl. We have 15 millimoles of the NaOH. We don't care about the water or the NaCl. HCl is our limiting reactant. we wind up with our hydroxide concentration being 5 millimoles now over 250 milliliters. So 5 divided by 250, that is a 0.02 molar hydroxide, or POH. Then is the negative log of that. That's 1.70 basically. So our pH is going to be 14 minus the POH. So that's going to be 12.3 for our pH at that point. So adding 49 more milliliters from question 4 takes the pH up from 10.7 to 12.3, not quite as dramatic a rise as you see, again, as a characteristic of that strong acid, strong base curve. All right, now question 6, we're looking at a weak acid. We've got acetic acid, and we're going to titrate that with NaOH, and we're asked the question, what's the pH after 0 milliliters of NaOH is added? Well, so at that point we only have acetic acid, and you can always, if you're dealing with a weak acid, you could just always call it HX or HA or something like that. I'm going to use the abbreviation AC for acetic acid, which is common. And what's going to happen if that acid is in water solution is it's going to undergo an equilibrium. It's going to produce some hydronium ion and give me some acetate ion there as a product. This is an equilibrium, though. We're going to do an ice chart. And, of course, if we're looking at acetic acid is AQ, water is a liquid. That means it gets left out. Hydronium ion is AQ, as is the acetate ion. So initially we've got 0.100 molar, 0 and 0 hydronium ion and acetate ion. What's going to happen? Q for that, of course, is 0 times 0 over 0.1, that's 0, that's less than Ka, which we're told is 1.8 times 10 to the negative fifth. So that tells us that this is going to go down negative x, and this will go up plus x and plus x. They're all multiplied by invisible ones because the coefficients in each case is 1, an invisible 1, so we don't have to multiply them by anything. To get the equilibrium line, we just sum the two, so 0.1 minus x for acetic acid, 0 plus x is x, 0 plus x is x. Now we're going to plug those in to our Ka expression, which is 1.8 times 10 to the negative fifth is our value for the Ka. That's going to be equal to x squared over 0.1 minus x, which is representing the hydronium ion, which is x, the acetate ion equilibrium concentration, which is x, and then on the bottom we have the equilibrium acetic acid concentration, which is 0.1 minus x. So we wind up with this little mathematical equation here to solve, and that would give us a quadratic equation. But remember that if the initial concentration is high enough and the Ka is low enough, such that the value of the initial concentration over Ka is bigger than 100, we can make a simplifying approximation. And that simplifying approximation is that the x on the bottom here is going to be so small that 0.1 minus x is basically going to be 0.1. And that's a valid approximation in this case. So if we do this, that tells us that x is going to be the square root of 0.1 times 1.8 times 10 to the negative fifth, and that value, I believe, comes out to be 0.13. Let's see, 1.8 exv5 negative times 0.1 square root, right, that's 0.0013. That is our concentration of hydronium ion, among other things. It's also the concentration of the acetate ion, but we want the pH, so we'll say pH is negative log of the 0.0013, and so that pH comes out to be 2.87 for that weak acid. All right, moving on to question 7. Now we've gotten a little further in the titration. Now we've added 50 milliliters of NaOH. And at this point, we're going to look at the one-way reaction where I have acetic acid reacting with sodium hydroxide. Sodium hydroxide is a strong base, so it's going to react. It's going to make water. We'll have a sodium ion, and we'll have the acetate ion. Okay, so the H from the acetic acid and the OH from NaOH get together and make water. Then we have the acetate ion left over and the sodium ion, which would balance its charge. Now, since this is a one-way arrow, we're going to do a BCA, not an ice, but a BCA. So we're going to, we're not going to worry about water. We're not going to worry about sodium, but we are going to worry about acetate. So initially here we have 100 milliliters times 0.1. That's going to give me, as I did in the problems above, 10.0 millimoles. And the 50 milliliters times 0.1 is going to give me 5.0 millimoles of NaOH. And initially we have no acetate ion. So one-way reaction, limiting reactant is going to be the NaOH. We're going to have 5 millimoles of the acetic acid react, and we're going to produce 5 millimoles of acetate ion as a result of this. And again, all of this, we have to take into account the coefficients, but fortunately here they're all ones, so it's -5, -5, and +5 on the product side. So we wind up with 5 millimoles of acetic acid left over, no NaOH, and 5 millimoles of acetate ion. Now, we've got both members of a conjugate acid-base pair present. That's a buffer. So we have a buffer because we have acetate ion and acetic acid present. That means we can use the Henderson-Hasselbalch equation. pH is pKa plus the log of the base concentration, which is our acetate ion, over our acid concentration, which is the acetic acid. Now, pKa, of course, is just negative log of 1.8 times 10 to the -5th. So for acetic acid, that comes out to be 4.74. And then if we're looking at the log of the concentration of the acetate ion, normally, you know, we would have calculated the concentration of the acetic acid and the acetate ion using the sum of the volumes, right? So what will look something like this. 5.0 millimoles over 150 milliliters. And then over here I'd have 5.0 millimoles over 150 milliliters. Now, what you notice here is that the milliliters, the volume here and the volume here, they're the same, and those would actually cancel out. So we don't even have to worry about the volume when we're doing this type of problem. Of course, here the 5 and the 5 millimoles cancel out as well. We wind up with 4.74 plus 0, so 4.74, and that's the pH, and of course that's the halfway to the equivalence point. pH is equal to pKa. That we wind up with that. Now, question 8 takes us to the equivalence point. And so we're going to look at the BCA again. We got the acetic acid. We got the sodium hydroxide. They're forming water, sodium ion, and acetate ion. Like so. And of course, you know, you should be able to do this for anything, any point in between, right? And if there have been more time on the quiz, I probably would have given you a little more, something in between the equivalence point and the halfway to the equivalence point, where you could see that the pH changes as the amount of base relative to the amount of acid changes. We're jumping to the equivalence point in this case. We're not worrying about water. Water's concentration doesn't change. We don't need to worry about the sodium ions concentration. But we are going to worry about acetic acid, sodium hydroxide, and acetate ions. So again, 100 times 0.1 gives me 10 millimoles for acetic acid, and now 100 times 0.1 gives me 10 millimoles for sodium hydroxide, and presumably no acetate ion is present at the beginning of this. But what happens is we look for the limiting reactant. We have double limiting reactants, acetic acid and sodium hydroxide both run out at the same time, and we make 10.0 millimoles of acetic acid. So this is acetate ion. So at the end of this, we no longer have a buffer. All we have is acetate ion, which is a weak base. So to get the pH at the equivalence point, we have to do the weak base problem. So the weak base problem is that the acetate ion can react with water, and that's going to form hydroxide and recreate some acetic acid. Water is liquid. All these other things are aqueous. This is how acetate ion acts as a weak base. Kb for the acetate ion is going to be Kw divided by Ka for acetic acid. So that's 1 times 10 to the negative 14th over 1.8 times 10 to the negative 5th. That comes out to be something like 5.6 times 10 to the negative 10th. We're doing a ice chart now, and we're not worrying about water because water's concentration is constant at 55 moles per liter. Initially, we have no hydroxide, we have no acetic acid. For acetate ion, we have 10 millimoles divided by 200 milliliters, which is going to give us something like, I believe, 0.05 molar. Let's see, 10 divided by 200. Yeah, that's 0.05 molar. Now, since this is an equilibrium process, we're not looking for limiting reactant. We calculate our Q here. That's going to be 0 times 0 over 0.05, which is 0, which is going to be less than Kb. So that means we have a minus here, a plus here, and a plus here. Coefficients are all 1, so we say minus x, and we wind up with x, and 0.05 minus x in our equilibrium line. Then we have to write the Kb expression. Kb, the value we calculated was 5.6 times 10 to the negative 10th. That's going to be equal to x squared over 0.05 minus x. And that comes from the hydroxide concentration at equilibrium, which is x, times the acetic acid concentration at equilibrium, which is x, over the acetate ion concentration at equilibrium, which is 0.05 minus x. So this is our little numerical equation we have to solve. And again, if you look, the approximation is valid for this. 0.05 divided by 5.6 times 10 to the negative 10th is much greater than 100. So we can say 5.6 times 10 to the negative 10th is basically going to be x squared over 0.05, because x is going to be so small that 0.05 minus x is going to basically still be 0.05. So x is going to be equal to the square root of 0.05 times 5.6 times 10 to the negative 10th. So let's see. 0.05 times 5.6 EXP10 negative. Square root of that comes out to be 5.29 times 10 to the negative 6. That's going to be 0.1234559. So you can see that that really is a lot less than 0.05. And that's going to be our concentration of hydroxide ion. So our pOH is going to be the negative log of that. And so that is 5.28. Our pH then is going to be 14 minus pOH. So that's going to be 8.72. So our equivalence point pH for a weak acid strong base titration is greater than 7, and to get that pH at that equivalence point, we have to do first the BCA analysis, then the weak base problem. So that's quite a long problem. That's the only point in a weak acid strong base titration that we have to do that. If you went past this point where you had a little excess in NaOH, then the NaOH would totally dominate the pH, and you could just worry about that to get the pOH and then the pH.